Welcome, ladies and gentlemen, to Integrated 2 Math. In part 2 of today's episode, we will be discussing the non-rigid transformations of functions. And so in the last episode, we talked about y equals x squared being a parent function, and we talked about how it's being shifted left, right, up, and down based on addition and subtraction happening either on the inside of the function, which resulted in a horizontal shift opposite your intuition, or a transformation on the outside, which was vertical transformation with your intuition. And today we'll be discussing the non-rigid transformations and doing a few more examples and putting it all together. So from here, if I give to you y equals, say, 2x squared now the transformation, unlike last time, deals with multiplication of values rather than addition and subtraction of values. So I'm going to go with -3, -2, -1, 0, 1, 2, and 3, the same numbers I've been using this whole time. And when I plug in a number like 0, I'll still get 0 because 0 squared is 0 times 2 is 0. 1 squared is 1, but times 2 gets me 2. 2 squared is 4 times 2 is 8. 3 squared is 9 times 2 is 18. And of course, a parabola is symmetrical, so these numbers will appear up top as well. So how does that impact our graph? Well, when I put my coordinate plane in here and I actually start pumping these numbers in, I'll go ahead and do it in black. What happens is I still get 0, 0. That's awesome, my center. 1, 2, -1, 2. And then 2 will get me all the way up to 8. And -2 will get me all the way up to 8. And by the time I hit 3, I'm way off the screen. And so from here, look at what happens to the parabola when the multiplication of 2 happens. Compare that to the original parent function. What's happening here? Well, my center has not changed, but the parabola seems to be narrower. It seems to be narrower by a certain amount. So narrower parabola. And that's somewhere. Okay, here we go. Yeah, it's in black, so it's hard to see on the board here. It's a narrower parabola. And I'll give you a hint as to how much it's narrower by. If you compare the numbers here, compare the 18 to the 9, compare the 8 to the 4, the 2 to the 1. In fact, it's actually a narrower parabola by 2. It's narrower by 2. Okay, let's go ahead and take a look at what happens if we do something a little more tricky on the outside of that parabola. This is something that you guys should hopefully have an intuition of, but it'll be difficult to multiply. If I do y equals 1/2 x squared, and I'll go and throw down those numbers here, and I think, again, you guys probably have a good sense of what's about to happen to this thing. 0, 1, 2, 3. I'll start at 0, which gives me 0. 1 squared is 1, giving me 1/2. 2 squared is 4, times 1/2 is 2. And then 3 squared is 9, so 9/2. So this is going to follow in suit like normal. And it's important to note that 9/2 is about 4.5, so we will keep that in mind when we graph this thing. So I'll go ahead and do it in dark green here. And so I think you guys will see what's happening here. I think hopefully it's relatively obvious. We get 0, 0, 1, 1/2, -1, 1/2, 2, 2. And then 3, 4.5, and then 4.5, oops, 4.5 over here. If you notice this parabola, what's happening with this parabola compared to the parent function? It's kind of hard to tell, but if you look at it really, really closely, you'll notice that this green parabola, the center, as always, is 0, 0, because we haven't done any kind of vertical or horizontal transformation. But it's wider, right? This thing is wider by a certain amount. It's wider or compressed. Wider or compressed. And I think we know why that's happening. It's because of that 1/2 on the outside right there. That 1/2 compresses it down. It's stretched horizontally of sorts, or compressed vertically. And so we could say that it's compressed vertically by 2. Some people say that it is vertically changed by 1/2. Okay, so from here, Let's see if we can come up with a generalization, because this one is actually very, very odd. When it comes to stretching, numbers on the, or rather, not numbers on the, numbers multiplied, and notice how the multiplication happened after the function took place, right? We always squared the thing, and then we multiplied by the numbers. I'm going to put that in our notes. Numbers multiplied after the function takes place stretch or shrink the function vertically. It's important to note the type of number that does this. What I usually say is large numbers or big numbers. Big numbers will vertically stretch the function. And I'll give you what that is in just a second. Small numbers will vertically shrink the function. And again, you have no idea what I'm talking about when I talk about big versus small numbers, but don't worry, I will give you examples of all of those, and that's why I'm making myself space. Big numbers are things like, examples of big numbers are numbers like 2, as you saw, 4, as you saw, 7 will make the graph vertically stretched. Small numbers are things like 1/2, 1/3, 2/7, 4/9. Now, before you come up with a generalization and say, "Okay, I get it. All fractions make the stretch shrink," that is actually not true, because an example of a big number would be 7/4 is considered a big number. 9 seconds, 9/2 makes a big number, making sure that the parabola is going to, or any function, is going to stretch vertically. So the way we generalize this is we say the a term, the absolute value term, if it's greater than 1, then you get a vertical stretch. And the reason why we do the absolute value greater than 1 is that if I break this up using my integrated 1 skills, it would be a is greater than 1 or a is less than -1. Now, don't worry about him for now. We'll talk about him in just a second. So if you're wondering about him, don't worry about him. We'll talk about what that negative does in just a second. In this case, a fraction whose absolute value is less than 1 will cause a shrinkage. And that's because using my integrated 1 skills, I would say then that a is in between -1 and 1. So hopefully that makes sense. We'll do a few examples, and then we will hopefully make sense of this. And we are back for the last transformation of all functions. So from here, let's go and just keep doing the same numbers we've been doing. And so here we go. I'm going to go and do this normally. And so what I get is, if I get 0, I get 0, 1, 4, 9, 1, 4, 9. But remember, this negative on the outside makes all of my terms negative, because that negative applies after the function happened to it. Imagine, if you will, multiplying the whole function by a -1 after squaring the function. So how does that affect my graph? I think you already know. So I will go ahead and compare him to something in blue. And so 0, 0, here we go. And I think we predicted this to happen, and it happened. So obviously, a negative on the outside, a negative, and I know we can't see that, a negative on the outside of the function flips the function upside down. Now, we will eventually talk about negatives inside the functions, which flip them the other way. And so, but don't worry about that for now. Just worry about the negative on the outside of the function. And those are all the transformations you're going to need to know right now. And so, putting it all together, if I had to describe the transformation abilities of this function here how I would describe it would be it's being shifted to the left by 3, it's being shifted up by 4, it's upside down, and it's being stretched by 3. And again, let's distinguish the 3's here. The 3 that shifts it is the 3 on the inside. The 3 that stretches it is the 3 on the outside. And so let's go ahead and do a quick little sketch of this graph here. So here we are. And I will go ahead and graph that real quick. So I've got left 3, up 4, like this. Upside down, stretched by 3. A stretch by 3 is pretty arbitrary. If it was just skinnier than normal, then I'd be fine. If I say sketch, then go ahead and sketch it like that. If we actually ask you to graph, please make a table and graph it. But that's pretty much how this thing culminates into, is all of you guys being able to identify a graph quickly. So I'll just do one more example, and I think we'll be able to generalize this pretty good here. So 1/5 x minus 2 squared, let's make him minus 7. So I'll go ahead and describe all of the transformations. I'll even type them out this time, that way you can actually read what I'm saying. We know that it's going to the right by 2. Move this dude over. To the right by 2. It is also down by 7. It is stretched by 1/5. And it's right side up, in which case you don't have to write anything. If it's right side up, then you would just assume that it's normal. And so from here, right by 2, down by 7 is going to be right here. And it's going to be wider. And again, wider, that's a pretty arbitrary kind of thing. So as long as you sketched it wider than your average parabola, I'd be totally fine with it. And again, if we ask you to make a table, please make a table and graph that one accurately. If we ask you to sketch something, I'll take a sketch, and that would be good enough. Hopefully this clears up the confusion when it comes to transformations. These are your non-rigid transformations, the compression and stretching and the flipping. As always, please leave questions or comments in the comments area, and I will see you in the next episode.